Hello everyone, welcome back to my tutorial. In this tutorial, we are going to solve the low cycle fatigue analysis using salome. I have taken a sample model of a dog bone shape. So one side I am just fixing it, other side I am just applying a force of 1000 Newton. It has, up to the elastic limit, it has a material property of steel with an Young's modulus of 210 gigapascal. And Poisson ratio is 0.3. So after the elastic limit, it is following the stress strain curve. So this one is the data, strain versus stress. And to calculate the life, so I have used a Manson-Coffin approach to calculate the strain. So I am going to apply a cyclic load, the reverse cycle. Now we will solve this model using salome. So first go to geometry model. I have created a geometry already. So first I am going to import the geometry. Step file, pictures. So this one, just make it S. So first check the dimension. It is in the meter. So now this is in the solid, here you could see. Now we'll create a groups to apply the boundary conditions. Create group. So this one is the fixed group. I'm just naming this as a fix. Just apply. Here I just want to apply the force. Just apply. Just close. Here you can see we have created the groups. First we'll find the area of this force here. So go to basic property. So this one is the surface area. Just copy. I'm just keeping this value here. Paste. This is just the area. Just keeping this here. Because in salome we cannot apply a force, we can apply only the pressure. So we have to convert this force into pressure. For that I have just calculated this area. Now we'll move into a meshing model to create the mesh. So before that I just saving this file. So just go to mesh model, select this mesh and create mesh. So I'm going to create a tetra element with simple parameter 0.002. Just compute it. Okay, so for study purpose I'm just keeping this coarse mesh. If you want to make finer, you can make it. So this is enough for me as of now. Now just check these groups are imported. Yes, groups are available. Now we'll just move into aster study to create the setup for fatigue analysis. Just say OK. First we have to read the mesh. First add a stage, read mesh. So this is our mesh. Just apply. OK. Model definition. It is a finite element model, mechanic 3D model. Just apply and OK. Now we have to define the material. For defining the material, so we have to define the stress strain curve function. Here you can see this function we have to define it, as well as this fatigue data function also. So for that, so first to define a function, the first function is stress strain function. So it has to be a strain here. Strain is nothing but EPSI, coordinate and edit. So this one is the strain and this one is the stress. So this data we have to type it one by one. So otherwise we can import it also. Here I have this file. So this one is the live file. So just close this. So we'll open one more file. Yes. So this is the strain versus stress data. This one is the Excel file. We have to save this file into .csv. So for that, just copy it, just go to new sheet and paste it at initially, then just go to file, save as. We have to save it as .csv file, text format, just name it as stress for easy understanding, stress strain. Just enter, save it. So it is a field delimiter of comma, just save OK. Now we have saved it. Now just go to here, we'll import the file directly because typing it will take time. So pictures, code aster. So this one is the file, just open it. Now you see we have this file, just say OK. This is a linear interpolation. Right side it is to be a linear and left side is the explosive. Just apply and OK. Now we have defined the stress strain curve. Similarly, we have to define the strain versus life curve. So just go to here, define a function. Life, I'm just simply giving life coordinate. Strain versus life, similarly. So x-axis is so we have to define the strain versus life. So how we can define is, so this is the stress strain curve. We'll save this and close it. First we'll check this file. Just OK. Yes, same way we have to import it. Strain versus life. So I'm defining x has to be a strain and y is to be anyway it will interpolate the values. So x I'm defining as this value also we can define, otherwise we can go for it as a coordinate also. So I'm just going for a coordinate. Here x coordinate is the epsilon. So edit, so we have to define the x coordinate here, or we can import the data also. So for that just go here. Here I have the file, I'm just opening. We have to save it as a separate file. So this is, I'm just rename it as strain, and this one is I'm just rename it as life. So for strain, just copy and paste it there. For life also just copy and paste it there. So we'll save this file separately. File, save as. This one is the strain. Just save it. And this one is the life. Just save it. So both the file I have saved it. Now we'll check the file. This one is the life. I'm just closing this file. So this one is the live data. This one is the strain data. Now just go to salome meca now. First just cancel it. So x coordinate has to be a life. So y coordinate is the strain. So here we cannot define life actually, strain only we can define. So better so we can define this one with strain. So here we have to import the data of strain, and here we have to put the data of life. That is the better way. So for that just go here and pictures, code aster, this book one, just open it. Yes. So book 1, it has multiple data files. Just cut it and paste it here, and this strain has to be opened. Just copy and paste it here. Now just save it and close it. Just save it and close it. Now we have to import this book 1. See, both the values are. Just copy, paste it here. Yes, just save it, just close it, and this also just close it. Now just check the values. Yes. So now we have to import this file. So just go here, pictures, code aster, LCF. This is the book file. So first one is the strain, second one is the life. So whatever it will interpolate based on the strain, whatever strain it will take. Just say OK. So this is any name we can give. So this is the log curve. Both are log curve. So x and y both are log curve. This is just make it linear interpolation, both side. Just apply and OK. So now we have defined the life curve also. Now just go to the material definition. Go to define the material. So here up to the elastic limit we have to define the Young's modulus and Poisson ratio 210 e power 9. Poisson ratio is 0.3. Density is not required. Now we have to define traction. So traction, I'm just choosing strain data. And we have to choose fatigue also. Fatigue. So this is the actually strain life approach. So for strain life approach, we have to use Manson-Coffin. If you are using a stress life approach, we have to choose Euler curve. But this one is the strain life approach. Here we have to choose this function. Just OK. Just apply and OK. Now we have defined the material. So this one the matter. So anyway, we can rename it also. So just renaming this value. Just say OK. The only thing is, so we have defined, see here, up to the elastic limit, we have defined Young's modulus and Poisson ratio. So for after the elastic limit, we have defined the stress curve by using a traction curve. Then after that, we have defined, for calculating the life, we have defined fatigue using Manson-Coffin curve. So now we have defined the material. Then we will assign the material to the model. Assign the material. Now this is steel. Just say OK. Just apply and OK. Now I have assigned the material. Then we'll create a time step to solve it. First we'll define the load function. Here it is a time. Edit. When time is 0, the load is 0. When time is 1, the load is 1. When time is 2, the load is 0. When time is 3, the load is -1. When time is 4, the load is 0. Now see the curve. So I have given this cyclic curve. So reverse cycle. Just say OK. So just apply and OK. Now I have defined the load function. Now we'll define the time rest real and 0. So up to the maximum we are tasked to solve. First what will define 0 to up to the 1. So up to 0.1 I'm just giving. So from 1.1 it is 0.01 I'm defining. Step is I'm giving 0.01. Then from 1.1 to see here, so up to this it will not diverge. It will, whenever the load applying, it will go. When suddenly we are changing the load, it will diverge. So to avoid the divergence, I'm just giving a minimum time step here. Then it will start converge. So it will go up to the 0, up to 3 it will go. So I'm just giving 3, 0.1, 0.1, then 3.1 up to 3.1, 0.01, 0.01 I'm giving. Then 4 up to 4 I'm just giving step length of 0.1. So just see, so this way I'm just giving by seeing here. So here up to 1 I'm just giving, from 1 to 1 I'm just giving this much, 1 to 3, so 10 and 8 like this I'm just giving. So by convergence, so I'm just giving more iterations here. So now just say OK, just apply and OK, and just go here and instant also I'm just choosing an auto method. This is 0.001 and this one 0.1. Just say OK, just apply and OK. Now I have defined all. Now we'll define the boundary conditions. So go to assign the mechanical load. First one is the BC. So assign the group of element is a fix. Just say OK. So I just want to fix it all, 0, 0 and 0. Say OK. Just apply and OK. Now I just want to apply the load. Load. So it has to be a force phase. A pressure also we can apply. So force phase, edit in X direction. So I'm just choosing this value. So it is a variable because we cannot directly apply a force. Pressure, you have to convert that into a pressure. So what is the force value is 1000 Newton, 1 e power 3 divided by the area value. So area is 0.4036. So 0.123436. So this is the pressure value, we have to apply it. Just apply and close. Just say OK. So I have given a positive value, that means it will start with tension. Okay, now it is correct. Just say OK. Now I have defined both boundary condition and load. Now we'll define the solver. Just go to analysis, static nonlinear. So this is the same one, and here we have to define the load. First BC, then sex load is the load 0. We have a multiplication function of load F. Just say OK. Then there is option called comportment. Here just choose relation is Van Mises isometric trace. Deformation, you just keep it this petit only. Just say OK. Remaining thing you just keep it simple. Global relaxation I'm just giving 1 e power minus 6, and this one I'm just making 15. Just apply and OK. Now I have defined the solver. Then what, we just want to take the stresses. So these two, sigma element and node, similarly SEQ element and node. Just OK. So this is unnamed, it comes same name, I'm reusing it. Then we have to calculate the fatigue data. First we will save this data. Set output results, format, we will navigate this file, pictures, code aster. So I'm just naming this result .rmad. This is just static nonlinear result data, it will save it here. Just save OK, just apply and OK. What it will do, it will calculate the static nonlinear data, it will save the results in first result file. To save the life or damage, so just go here, this one we have to do it. For that we have to calculate the LCA epsilon data, we have to calculate it. So just go here, just simply small data, just add it here also. Deformation EPSI Helga, yes, this one we have to choose. And one more thing is there, yes, this is enough. Now just apply and OK. Now here also, yes, now we have calculated the strain. From the strain we have to calculate the damage. So for that just go to, first we will solve this case. So if it is solved correctly, then we'll calculate fatigue data separately. So now just go here, make it 5 seconds. So I'm just giving more memory, just run it. Just wait for a while how it is solving. If it is any divergence occurs, we have to reduce the time step to solve. Now it is started reading the command file. Oh, nicely it is solved, and yes, nicely it is solved without any error. See, so it is solved nicely. So this way it is done. Now we'll see the results. Just go to paraview, pictures, code aster, result file, just open it. Now we'll see the displacement. First read the data, just go to other one, then just come to this one. Now we'll animate this value with the deform shapes. I think it is not solved properly, it seems. Yes, now this is the way it will do the deformation. Now we'll check the stress value, actually von Mises stress. So we are getting a 43 megapascal maximum. So this way it will animate. Some 500 I'm using. Now we'll animate again. Yes. Now animate again. Yes. So now the applied load value is also correct. Now we'll check with the. Now we'll calculate the damage. Actually, paraview takes time to read the data, so that's why it's showing that way. And other way also we can check it. Just go to filter, search, just do the plot data with the time, just enter it. So here we have to choose some nodes. I'm just choosing here, just apply. Now just go here, you have to choose the maximum value. Here instead of time we have to choose the strain data. Strain is not, we are not calculated. Anyway, by time we'll choose displacement x. When time is, why it is solving, it's going maximum of 0, 1. Up to 4 it is solved, but it's not a negative value, it is not solved. Just check the command file again. Now we'll see the animation again. Yes, the load data is correct only. Now we'll plot the data. Plot. Just OK. Select any one of the node here. Just apply. Go to plot data over a curve. X is the time. Y has to be a displacement in x direction. So this is, I'm making this into maximum. So only maximum it's showing. So average if you take, you will get it. Yes. So this is the way it is applying the load. So now what we want to do, we just want to calculate the damage from the cycle. Go to aster study again. Now just add a stage, one more stage, case. Here just add a one more stage. We just want to calculate the damage post processing. Here there is option, here calc for tick. So cumulative damage, here we have to use the option called DOMA LCA epsilon history. From the calc champ we have to calculate. This one is the invariant sign. Damage, here we have to choose mansion coffin. Material is steel data. This is we have to choose life function. Just apply and OK. Now I have chosen all. So it is just named as a field. I'm just naming as damage. So to easy understanding, because it will calculate the damage only. Now we'll save the data. Just go to output, set output results, navigate the file. damage.rmad, edit. Here mesh, instead of result we have to go for field. Then here taucham s. So this is we have to do it. Now just say OK. MAD format, just apply and OK. So now, so this is stage 2 I have set it. Now just go to the history view. Now here you can see we have solved the first case. From the first case we have to reuse the data. We should not run the data this again. So here we have to run the data. So it will take the data from the first case and then it will run. Then just run it. So now it is come up with the error. We will check, we will read the message. What is the error? So EPEQ LGA is not available in the data. So for that what we have to do? We have to calculate the EPEQ LGA in the first case. So just go to here, calc champ. So in deformation we have to choose EPEQ LGA. See, not here. So this is actually deformation. In criteria, just go to here. There is an option called EPEQ LGA. This one we have to take. So this is the equivalent strain it is taking, from that it is calculating. Just apply and OK. Now thing is we have to rerun the first case also. So just go here. So instead we can go here. Both the case we have to run it. Just save the data, just run. So it will keep the files. Now it is running both the case simultaneously. First what it will do, it will solve the first case, then it will solve the second case. That is the way it will do. See, it is completed without any error. Now we can see the damage. So just open the file. So 73 LCF fatigue. Here there is a file called damage. Yes, just open it, just apply. Now see, damage is calculated. Now here you cannot see the damage because it's a Gaussian value. So just go to filter, mechanics. So LGAR to surface, we have to take LGAR to surface, just apply. Now just go here. Now you can see damage. So this is the damage value. So this is the damage value. Here you can see the red is less damage. So this is the damage value. Now we will see the life of this component. Life is nothing but 1 by damage. Just go to filter. There is option called data calculator. Just 1 divided by damage. Just apply. This is nothing but result. Here we can name it as life. That is better to understand. Now see, the life is there. Now here the lives are more. Here the life is less. In damage itself we can see it. Here damage is more. 6.1 e power minus 7. It is minus 8. Here damage is more. Here damage is less. So to see in a better color. So here damages are more. Here damages are less. So similarly, calculate also we can change the color. So this is a way we can calculate the life. This is actually coming, life is more. That is because the load is very less. If you apply more load, you will get very less. So based on the strain, it will calculate the life. So this is the way we can do the low cycle fatigue. This is actually a life. It is coming 1 lakh cycles. The life is more actually. If you increase the load, so instead of giving 1000 Newton, so by 20 if you add, it will go for plastic region. So based on the plastic region, it will calculate this life. So stress is coming very less. That's why life also very more. So this is a way we can do the low cycle fatigue. Thank you for watching my videos. Please subscribe my channel for more videos. Thank you.